Renowned physicist Michio Kaku has been closely examining the latest discoveries from the James Webb Space Telescope, the Dark Energy Spectroscopic Instrument, and the increasingly puzzling phenomenon known as the Hubble tension. His findings have led him to issue a serious scientific warning that challenges everything we once believed about the future of our universe. Recent data from the JWST, DESI, and ongoing Hubble research have sparked intense debate among the world's top cosmologists. The mounting evidence suggests that there is a fundamental misunderstanding about how the universe is expanding. As Kaku himself has remarked, even high school textbooks might need to be rewritten, and what follows will explain exactly why. A crisis is emerging in cosmology, one that threatens to upend the foundational principles of our understanding. Scientists have developed two highly reliable methods for measuring the universe's rate of expansion, but these methods yield completely conflicting results. When analyzing the pristine radiation from the early universe captured by the Planck satellite, the expansion rate is calculated at 67 kilometers per second per megaparsec. However, when astronomers measure distances closer to home using Cepheid variable stars and type Ia supernovae, they find a much higher rate, between 73 and 74 kilometers per second per megaparsec. Though a difference of 7 units might seem small in cosmology, this discrepancy is catastrophic. Both measurement techniques have been refined to extraordinary precision, yet the gap continues to widen. Initially, scientists hoped the discrepancy was due to errors in measurement that could be corrected with better technology. But that hope was dashed in early 2024, when teams using the James Webb Space Telescope conducted a triple check on these measurements. Leveraging JWST's powerful infrared capabilities, they refined distance measurements to Cepheid stars with unprecedented accuracy. The result was a firm confirmation of the higher expansion rate, beyond any doubt. This meant that the so-called Hubble tension is real and not going away anytime soon. Nobel laureate Adam Rees, who led one of these pivotal studies, gave a sobering assessment. With measurement errors ruled out, what remains is the exciting but unsettling possibility that our understanding of the universe itself may be fundamentally flawed. But that is only the beginning. What JWST uncovered next left scientists utterly speechless. Galaxies in the early universe that shouldn't exist according to current models. Designed to peer further back in time than any previous instrument, JWST revealed galaxies dating back just 300 to 400 million years after the Big Bang. The shocking discovery was that these galaxies were not tiny, primitive structures as predicted. Instead, they were massive and mature, exhibiting complex formations far too advanced for such an early stage in cosmic history. According to standard cosmological theories, the early universe should have been a slow, dark period where small building blocks gradually assembled into larger galaxies. Instead, JWST found galaxies brimming with stars, heavy elements, and intricate structures, indicating rapid star formation when the universe was barely 3% of its current age. NASA teams were stunned, with some astronomers describing this new population of galaxies as unexpected and electrifying, forcing a fundamental rethink of galaxy formation within the first 500 million years. By 2023, JWST had identified many more bright ancient galaxies than scientists ever expected, challenging decades of assumptions about the timeline of cosmic structure formation. If these galaxies truly existed, it meant that our understanding of the early universe required serious revision. Researchers from MIT and the University of Texas believe they may have found a single explanation that could solve both the Hubble tension and the puzzle of these early galaxies. Their groundbreaking work, published in late 2024, proposes the existence of an early dark energy burst within the first 50,000 years after the Big Bang. This early dark energy was not the same as the dark energy known today, but was a much more powerful force that briefly dominated the universe before disappearing completely. If the universe underwent a period of accelerated expansion very early on, this would have effectively shrunk what scientists call the sound horizon, essentially recalibrating the cosmic measuring stick used to estimate distances. This adjustment could finally reconcile the conflicting measurements of the Hubble constant, resolving the long-standing tension troubling cosmologists. Moreover, this early burst of energy would have paradoxically led to earlier formation of galaxies. As the burst subsided, the universe would have become slightly older and less dense sooner than previously thought, creating ideal conditions for the rapid formation of those massive early galaxies that JWST discovered. Simulations from the MIT team show that incorporating this early dark energy component produces numerous bright galaxies at very early cosmic times, perfectly matching JWST's observations while also bringing the expansion rate measurements into harmony. This elegant solution connects multiple cosmic mysteries through a single, dramatic revision of our understanding of the universe's infancy. However, the story becomes even more complex. New data suggest that dark energy itself might be evolving over time. In April 2024, the DESI team released findings that shook the physics community. DESI has created the largest three-dimensional map of the cosmos to date, charting millions of galaxies across billions of years of cosmic history. Their analysis challenges one of the most basic assumptions about the universe, that dark energy is a constant force. For decades, dark energy was thought to be an unchanging, steady influence driving the universe's acceleration, pushing space apart with a consistent strength. But DESI's data reveals subtle irregularities in galaxy distribution that don't fit with this picture. Instead, their measurements suggest that dark energy's influence may have gradually weakened over cosmic time. Adam Rees, co-discoverer of dark energy, called this discovery the first significant clue about its nature in 25 years. The implications are profound. If dark energy is losing strength, the expansion rate of the universe may not be fixed. Instead, the cosmos could be shifting from accelerated expansion towards something entirely new. Multiple independent observations support this unsettling trend, a slow decline in dark energy's power. While more data is needed to confirm this, it could signal that the universe's expansion is beginning to slow down, or even reverse. As this mystery unfolds, another line of evidence offers a fascinating confirmation of our cosmic understanding. Einstein's theory of relativity predicts that, due to the universe's expansion, distant events should appear to unfold more slowly than those nearby, a phenomenon known as time dilation. This effect acts like a universal clock, ticking more slowly in the distant cosmos. For years, attempts to detect this cosmic time dilation yielded confusing results, especially from early studies of flickering quasars. But recent breakthroughs have changed that. In 2023, a team led by Geraint Lewis observed ancient quasars from when the universe was just 1 billion years old. They found that time at that epoch seemed to pass 5 times more slowly than it does now, exactly as Einstein's theory predicted. Similarly, extensive studies of distant supernova from the Dark Energy Survey showed clear evidence of time dilation, with light curves stretched precisely as expected. These findings provide solid proof that the universe's expansion is very real and not some illusion. This precise cosmic timekeeping offers an incredibly sensitive tool for detecting unexpected changes in the expansion rate over time. JWST continues to push these observations to their limits, recently confirming a galaxy from only 280 million years after the Big Bang, the earliest cosmic clock ever observed. But if time itself is stretching in unforeseen ways, it raises profound questions about the ultimate fate of the universe. Throughout his career, Michio Kaku has explored 3 classical scenarios for how the cosmos might end: the Big Freeze, where the universe expands forever, stars burn out, and everything fades into cold darkness. The Big Rip, where dark energy grows so powerful it tears apart galaxies, stars, planets, and eventually atoms themselves. And the Big Crunch, where expansion reverses, causing the universe to collapse back into a fiery singularity. For decades, the Big Freeze seemed the most likely, as dark energy appeared constant, dooming us to eternal expansion and cosmic winter. But the new findings force scientists to consider something far more complex: a dynamic, evolving fate for the universe. If dark energy is indeed weakening over time, as DESI data suggest, the future could be far less certain. The force driving expansion might gradually fade, eventually halting cosmic acceleration entirely. Over trillions of years, expansion could slow to a crawl and stop, leaving a static cosmos where galaxies coast quietly to their final positions. Even stranger possibilities arise if dark energy continues to weaken or even reverses, turning from a repulsive to an attractive force. This could trigger cosmic contraction, with galaxies rushing toward each other, the night sky brightening as structures blue shift, and ultimately a big crunch that might spark a new Big Bang, starting an endless cycle of cosmic rebirth.